So, so far we've been talking about that the Schrödinger equation applied to the hydrogen atom gives as a solution the atomic orbitals. Those atomic orbitals have the shape that you have seen and it has some nodes. However, it may be good to understand why is it that why are those terms like 2s, 2p, 3d, why there isn't something called 2f, why there is no 2f orbital. That comes from specific restrictions that when we look at the function of the atomic orbital, that they may be more or less evident. As we said, this huge form, what the atomic orbital looks like, and this is still simplified. In here you will see some trigonometric functions and some exponentials that do not concern us, but it's important to see that the atomic orbital depends on specific factors. It will depend on what we call quantum numbers, three different quantum numbers. The different quantum numbers that we will talk about is n, l, and m sub l. The name of these quantum numbers, n, is called the principal quantum number, and it refers to the size. N refers to the size of the orbital, and it's called the principal quantum number. Then you have L, called the angular momentum quantum number, and that refers to the shape. So an s orbital or p orbital, it will imply it has a different value of L. And finally, the m sub L, and that's the so-called magnetic quantum number, that refers to the orientation. So when we talk about the px or py, that because they have different orientations, it's because they have a different m sub L value. So that will be the orientation. Okay, so there is some restrictions for these values, and I want you to look at, just for example, at what these factorial numbers inside of a root square. Notice that to make a factorial, your n and l, the ones that determine the size and the shape, must be integers. Otherwise you cannot do a factorial. And also notice that because these numbers inside of a root square, n has to be larger than l minus 1. So n has to be larger than l minus 1. Right? So otherwise, if L is larger, what's going to happen? You're going to have a negative number inside a root square, and that gives an imaginary number. It's not a real function anymore. Okay? And for the same reason, n can only be positive. So there is a fair amount of restrictions that we will just organize in a set of rules, but that explains why, for example, we don't talk about a 2d or 2f orbital. It's because there's some restrictions as for what shape and what size can be combined. Let me also remind you that when L is equal to 0, we call that an s orbital. When L is equal to 1, we call that a p orbital. L equals to 2, d orbital, L equals to 3, it's an f orbital. These letters come from the spectroscopy. Those lines coming from transitions with these orbitals were either the sharp, principal, diffuse, and fundamental. Okay, so what are these rules? Let's put them all together. The rules. What we said is that the principal quantum number n can be either 1 or 2 or 3 or 4 and so on. Okay. When you choose 1n, so first of all, an atomic orbital will be a specific selection of n, l, and m sub l. Okay? Can we choose any combination? No. This is what the specific restrictions of quantum numbers that we are talking about. So if you choose a specific n, say we're choosing for 2, notice that l can only be 0 or 1. It can go all the way to n minus 1. If we decided that n is equal to 2, L can only be 0 and 1. It goes all the way to n minus 1. So 2 minus 1 is 1. Okay? This is why there's only a 2s and a 2p. Because when L equals 0, that's called a 2s, and L equals 1, it's called 2p. There is no 2d because your L cannot be higher than n minus 1. And as for magnetic numbers goes, so if your L is 0, your M sub L can go from negative L to plus L. But that means that M sub L can only be 0. If L is 1, M sub L can go from negative L to plus L. Negative 1 going through 0, plus 1. Now we know why there is a 2px, 2py, and 2pz. Because when L equals to 1, the orientation, the magnetic quantum number, can be negative 1, 0, and plus 1. So let's run a question here. How many orbitals are found when n equals 3? Well, let's see. When n equals 3, we choose already one n, and probably from your previous courses you already know the answer. You already know that it's going to be 3s, 3p, and 3d. And probably you already know that there is 3 orbitals in the 3p and there's 5 orbitals in the 3d. And there's only 1 in here. So you know that. But you have to explain that also in terms of the rules of quantum numbers. Let's see. So if n is equal to 3, it means that L can either be 0, can be 1, or can be 2. It cannot be 3 because it can only run all the way to n minus 1. So in this case 3 minus 1, 2. It can only run to 2. And for each of those, for each value of L, M sub L, the magnetic quantum number, can go from negative L to plus L. Well, negative 0 plus 0, there's only 1 0, 1 M sub L. We call this the 3s. We found 1. When L equals 1, this can be negative 1, 0, plus 1. That's what we found, the 3px, 3py, and 3pz. Okay, and when L equals 2, the M sub L can go negative 2, negative 1, 0, 1, and 2. There you go. You've got the 5 orbitals from the 3D. Hopefully that makes some sense. We will practice more in class.